this one. Okay, so we have started a review of the ending of Calculus 1 with the, so this is the whole review of the derivative is right here. So, well, it's pretty much it. So you have the idea where it comes from. It comes from the quotient over there on right. So difference quotient called the average rate of change, called the average velocity if it's about motion, and then the next step is taking the limit. The result is you call it instantaneous velocity, you call it instantaneous rate of change, you call it the derivative. Okay, so the only part that's missing here is that this little thing happens for every single point on the graph of the function. So that tangent line is found for every single location on the graph. So that's certainly a challenge. So every point is accompanied with a tangent line. The slope of that tangent line is our derivative. Okay, so that is the review of the derivative. And slightly more time we're going to spend on the integral. Okay, so it is a reversal. And instead of trying to find the velocity from your location, we are finding location from velocity. Okay, so that's the displacement is velocity by time, and if you start adding up these things over different periods of time, you end up with what we call the Riemann sum, and the limit of the Riemann sum is the Riemann integral. Okay, so we still want to, this is what we talked about last time, and that is the Riemann sums of what? Of a circle of radius 1. Rather technically, it is the function that gives you the upper half of the circle. Let me write it. So f of x is equal to square root of 1 minus x squared. X between -1 and 1. Okay, so it applies to this setup over here. Taking the origin, making sure that the graph lies entirely above the x-axis, split the domain into little pieces, build the rectangles, compute the areas of those rectangles with Riemann sum. So multiplication of the width times the height. Okay, and just like that picture on right, kind of stretched out picture on right. But here we're doing it indeed 20 times for the interval. So technically, what we have found here. So as I pointed out, this. Okay, let me once again show you. I'll show what this is. So these are the values of x found between -1 and 1. These are the values of y found by the formula I just wrote. Okay, and then in the next line over here, I find each term of the Riemann sum is located in the next row, which I'm pointing out, which is so the product of the width. The formula is a little bit small over there at that little window over there, but you can see how that what's in parentheses is the width of the rectangle, and just difference of two consecutive values of x, and multiplied by the height, which is found in the column marked y. Okay, so that gives you one area of those rectangles. Not technically these rectangles, because these are, well, they are kind of narrow. In fact, let me try. I think there is a way to have a better illustration of this. I thought there was a, okay. I'm trying to make them wider. Are they getting wider? I think they're getting wider. Yeah, so the point being that if you really want to speak of rectangles, these are rectangles, the actual rectangles. So it's certainly just a visualization, although done by Excel, but you can see now the widths and the heights are here visible. The curve is not. I would have to add a curve to this well, maybe next time, but you can certainly see how we are sampling our circle with at the right end. So see that leftmost point at the bottom is in fact there is no corresponding point there, right? Why is that? Because well, because there is no point there, but actually the graph is sampled fairly high above that point, above the x-axis. Okay, so these are the areas have been computed, and finally the Riemann sum is over here, computed as you can see with operation, which is coincidentally called the sum, and it's, as you can see what is sum of the areas, and the answer is, as you can see, very close to the exact value, which is pi over 2. Okay, so if we would, well, let's make this specific. This is actually the right-hand Riemann sum with 20 points. Okay, so right-hand Riemann sum with n equal to 20. Well, not 20 points, 20 intervals. Okay, so it runs from 0 to 20, and that's how we get 21 points, and 20 intervals. Okay, now what I'm going to do next, I'm gonna have, how about I have now also areas, but I want to have left hand. Okay, so these are right hand Riemann sums in this column, and now I'm going to do left hand Riemann sums, which means that they will be running like this, from here, from the leftmost point to one short of the rightmost point. So that's where the our function is sampled. So from 0 to 0.9 over there, from 0 to 0.9. So this one is from negative 0.9 to negative 0.9 over here to 1. Okay, so these are where the values are sampled. These are the x values here. Now I'm going to sample them over here, from here to there. Okay, but the formula is the same, naturally, so just let me just, how should I do it? Okay, let's see, what do I get here? Okay, so I will take, okay, I'll put it here. So these two give me the difference of the values of the, of the axis, which gives me the width. Okay, so that is still in parentheses over there, and then it's multiplied by the value of y, and the value of y is 0, so that's why this is 0. But otherwise, these are the values. I spread them down. Okay, so these are the values of the Riemann sums in each of the intervals, but it is a left-hand sum. Okay, so so what do you think is the relation between the left-hand sum and the right-hand sum with the same number of points?
Have the exact same area.
Why?
Because the circle symmetry across the y-axis.
That's right, as a matter of fact. So generally we don't expect that to happen. But see over here, I did the left hand and I did the right hand. The difference between them is, first of all, they build from the same rectangles. They build from the same rectangle except for the leftmost, rightmost. So either we include the very first one and exclude the last one, or we include the other one. We exclude the first one and include the last one. Because of the symmetry, those are identical, and that's why the results over here, the right hand, these are two lines over here, two cells over here. The right hand followed by the left hand, and they produce the same exact result. Why? Because of the symmetry. Generally speaking, it's not the case. Okay, so you can certainly change the formula and realize that it's not the case. Okay, so one more thing I want to do here is increase the accuracy. I'm going to increase the accuracy, and I will move from 0.5. Let's do twice as accurate. So my width will be 0.05. Okay, so as you can see, what we end up with is no more than just a half of the rectangle, that half of the circle. So I'm gonna go farther. I need more data. Okay, so I am going up to 1. So I'll have to kill these. Okay, so these are my Riemann sums. Once again, this is a column filled with the rectangles. Let me first visualize them. Here they are. Okay, so same circle, but we have instead of 20, we have 40 rectangles. Okay, so then the result over here that I have produced over here is not our 20 anymore; it's our 40. Okay, let's see. So I have to recompute it. As you can see, I'm only doing half of it. So I have to once again stretch the data all the way down. Okay, like this, and then just look at the result, and the result is let me kill this. As you can see, it is it was 155, right? It is 156 now. Okay, so the accuracy improves with every with increased number of intervals or the decrease width of the interval. You can certainly compare. This looks much more like a circle than the one we started with 20. Okay, so all right. So that is the numerical side of the story. So which is very important because, well, let's demonstrate why it is important. Because after we take the limit, this is the total area of the so the integral, the area is the integral f(x) dx from a to b. In our particular case, the circle is the integral from -1 to 1 of 1 minus x squared dx. Okay, so we skip to the Riemann integral from the Riemann sum for the limit. And okay, so here either n goes to infinity or delta x goes to 0. Either way, we get the same result. If obviously there's a limit, so the limits sometimes don't exist. But we're not going to talk about that. Remember under what circumstances does the integral exist? It depends on the nature of the function. What kind of functions do you know that behave well? Continuous functions. Continuous functions are integrable. So as long as that function f of x over there is integrable, continuous, we have that limit exists, and therefore the area makes sense. Okay, so the area makes sense. It's when the function is poorly behaved, and even though we have the graph, hypothetically, if we try to figure out what is that area represents below the graph, it might be meaningless. At least meaningless in terms of the area. It has no area. Not that it's 0. No, it means that the area is meaningless. So in this particular case, when the function is continuous, it is like this. The area does make sense to begin with. Also, however, remember that it does not have to be continuous in order to be integrable. For example, you can have a function that has gaps like this one. So it changes abruptly. However, the area still makes sense. Okay, so anything that made of continuous pieces will be also integrable. Okay, so the circle certainly is integrable, as we know. That function is continuous. The curve is, well, visibly continuous. At least that's what we conclude. And then so the integral exists in itself. So we are then justified trying to solve the problem. We then try to evaluate the integral. The integral is itself. Then, so how to evaluate? And if you took Calculus 1 last semester or some point in the past, usually this is not something that you can easily evaluate with some an obvious method that's available. Okay, so the typical method of the most important method of integration is substitution, and the substitution works. So So use substitution. We don't have other methods. Okay, so what is the idea behind substitution? What do we substitute, where, and why? That's right. So the point being is that our function is kind of a complicated 1 minus x squared. Not just complicated, we actually look at it carefully and we realize this is a composition. It is a composition, and which means that it is computed into consecutive steps or more. So when you start with x, then you take x squared, then you do 1 minus x squared, and then you take square root of that. So, okay, so it is 2 or 3 consecutive steps. And then to make things easier, we could break it into pieces, such as y is equal to square root of u, and u is equal to 1 minus x squared. Okay? So that is the same function, composition of these two functions. So this is the composition of these two functions, of these, and which gives me the function that we're supposed to integrate. And then the idea is to try to replace integration with respect to x with integration with respect to u in order to, hopefully, it will be simpler. So how it goes on from this point is we compute, since our integral contains dx, it contains dx, so this is integration with respect to x, and we want the integral to be with respect to u. So we want to convert this somehow into integral of something with du over here. Okay, so this du is indicate that the integral is with respect to u. Okay, so then this is the hardest part of integration by substitution, is conversion of one du to another one. And the method that you might remember is to literally compute du in terms of dx, because there is already a relation between u and x, very explicit relation. Before you start worrying about the square root, you have a relation between u and x, which is given by this function, so which means that we know the derivative of one with respect to the other. Okay, so du dx is what? 1, there is no, just negative 2x. Okay, so then du is equal to negative 2x dx. Okay, so that's the idea of, and then if you wanna, you wanna carry out the substitution. So in the original integral at the bottom, I'm ignoring the limits of integration. We need to get rid of dx, and we can. Now it will be dx is equal to du over negative 2x. Okay, so that is the, there will be two substitutions. One is, so integral 1 minus x squared dx. So x appears twice, and we need to get rid of this, and we need to get rid of that, or rather that. Okay, we know that this is u. That's by design, 1 minus x squared, all right? And now we know also what dx is. It is du over negative 2x. Okay? So the substitution actually takes to 2 or more steps. At least every x is taken care of, and then dx2. So it's a literally substitution as if it is solving equation and just substituting values. So it will be integral square root of u, and I'm just substituting du divided by negative 2x. Okay, so what do we do next? Yeah? No, there's a problem. What about x? What do we do with x?
You solve it in terms of u.
That's right. The problem is why I refer to a problem because the substitution is unfinished. We were trying to get rid of all x's, and we haven't, and we still have x, so we cannot even start treating this as an integral with respect to u until all x's are gotten rid of. So x is not removed, so we have to do that. And so what is x in terms of u? Fortunately, once again, we have this taken care of. At least u is expressed in terms of x, and we can certainly do vice versa. And so the conclusion then is what is x from that little equation?
Square root of 1 minus u.
Plus. What plus is it? 1 plus u, right? X squared, well, no, it is minus.
Right, 1 minus u.
It is minus, yeah. Minus 1 minus u. Okay, so then yet one more step, one more substitution to carry out. So this was our concern over here, and now we know what to do. So one more substitution. So here we did 2 substitutions. One more substitution. So we have integral square root of u du negative 2, and here I have 1 minus u. Okay, so well, substitution is finished. Okay, so as planned, the integral was with respect to x. We have a new integral with respect to u. We need to now evaluate it. Okay, let me try to sort it out. Negative 1/2, and here integral u over 1 minus u square root du. Okay, so what do we do with this one? If you know. So who knows what to do with it? Yeah?
Split the fraction.
But it will remain inside of square root. Well, let me ask you this before we proceed. What do you do if you don't know how to solve an integral? Well, right now, you need, your life depends on it, and you're supposed to do something. What would you do?
If we didn't know how to solve that, and we've got that answer.
It's not the answer. We're not done. So what do we do? What do you do? No, outside the box. You don't know what to do, and you are just not ready to proceed. What is your way out? There are 2 ways out, actually.
You can put it back in terms of x again.
And start over, in other words. Okay, but maybe. But you are still trying to solve the problem that you just admitted you don't know how to do, how to solve it. One way is, like, I can see I only see 2 persons with the solution, one and the one person behind you. What do they have in common? Over there. The book, the back of the book. Yes, the answer is in the back of the book. So just about every integral we're going to encounter, or at least half of them, will be found in the back of the book. So if you're stuck, go to the back of the book. You can go ahead and do it. Well, I just don't want to do it, but that integral, the original one, in fact, this one, is in the back of the book. Okay? There's one more. That is, everybody has that solution. You can find it online, obviously. And then there's a third one. The third possibility is this. We didn't waste our time doing this, so if you cannot solve the problem and you can find a solution to that integral anywhere, remember that we're talking about areas, and you can always approximate area with the Riemann sums, And there you go. You have at least you have an approximation of the answer. So we are right now after the exact answer. After all, we know that the answer is supposed to be pi over 2. We know the answer, we cannot prove it just yet, but at least we can approximate it. Okay, so that applies to every single formula we can think of, because look at it, this one is pure algebra. You don't need any integration, differentiation, you don't need substitution. This is, all you have to do is just look at this part over here and replace the formula, not this one, this formula, okay? Replace the formula with the function that you care about. So this one was more or less square root of 1 minus x squared, which what we're talking about. But you can think of any other function that you don't know how to integrate. Well, straight up there isn't a way to approximate it. Okay, so that said, there is a way to solve this problem. But once again, don't remember that in this course and in every other course, the Calculus 2 in the textbook, the problems have been selected in such a way that they can be solved always. Okay, so pretty much always there is a way to solve it. However, if you pick a function at random, you probably cannot do it. So you can make up make up a function easily that it looks so intimidating that it certainly cannot be integrated. Okay, nobody can probably. Okay, so in real life you don't have this luxury, and you will be facing integrals if you ever that you cannot evaluate. So don't resort to trying necessarily find a way like this. Thinking about substitution or anything like that, it might be simply impossible, but there are ways to do it, and the number one is always approximation. Works every time with every function. So, but we are obligated with this one. We are obligated because we have known from like third grade that the area of the circle is pi r squared, right? So, and we have known it forever, and now just only now it is time comes now finally to actually prove it. So we do have to evaluate this, but that is the main motivation is to finish this integration of this integral, but somehow an approximation doesn't do that anymore. Approximation is fine as far as the approximations are concerned. Maybe in real life they are more likely to be useful, but this is a fact from a long time ago, so like 2,000 years ago. So we want to prove it, and then turns out let's examine what we were trying to accomplish here. We had an integral. We did substitution in order to simplify it, and I have to say it does not look any simpler. Compare the integral at the beginning and the circles there, and this one. It's not really that simple, even though we can try to split well, there is really nothing to be split, I'm afraid. It is what it is. So there was no fraction, and now there's a fraction. It doesn't look any better. So I have to say it's not better. On one hand, on the other hand, we didn't make any mistakes. So we did carry out the substitution. So that's when learning how to do substitution. This is the crucial part. Well, there are two crucial parts. One is to be able to carry out the substitution, which we did, and finished it, and then the second part is choose substitution wisely. Okay, so because even though the computations were correct, our choice of substitution it appears to be unwise, because we ended up with something that is just as complicated as the original. Okay, so once you understand that, you start looking for another substitution, and the substitution, unfortunately, is not obvious. But let me step back and just remind you from last semester that this was a correct method. There is nothing wrong with it. Say, for example, if I had integral x square root of 1 minus x squared dx. It's almost identical function, except I have an extra x in the beginning. Okay, so the substitution then is the same. Therefore dx is still the same value, du over negative 2x. Okay, and you can see how things work out. Why? Because the problem is designed in such a way so that things would work out. So you see what happens? What is it equal to? I'm doing substitution. I replace 1 minus x squared with u, and I replace dx with du over negative 2x. So what's the end result? Well, let's write it out. X squared of u and du over negative 2x. Getting rid of x is easy because it simply cancels out. And we end up with negative 1/2 square root of u du. So does this look familiar? Integration by substitution, right? Okay, so once again, the idea was exactly the same. We saw composition, and we tried to split it into, well, this splits into consecutive steps. The first step, which is 1 minus x squared, is chosen to be the new variable u. Okay, and then we found that as u. Then we found du by the same formula as previously. We substituted, but then by magic, pretty much, we ended up with no effort and no extra work. We ended up with integral with respect to u entirely. Not only that, but what can you say about this integral in comparison to the original? It is simpler. So this one is better. Unlike the previous example, this one is better. In fact, well, how do I integrate it? Square root of u, what is it? Right. So what is the power?
Add power of 1.
Well, first you realize that square root is 1/2 power of 1/2, right? And then you integrate by the power rule or power formula, indeed. So what is it? U
3/2
over 3/2 plus c. Okay, and this one was at this point was substitution was over. Now integration over. Okay, there is one more step. What's the last step?
Change the 3/2 to the 2/3
Change u to back to
Yeah, back to x, right? So back substitution. So because the original was with respect to x, u was made up. We made up that variable u. It has nothing to do. Even the letter was made up. I could have put y there or z. And so the answer has to be in the same language as the original, so it has to be with respect to x, so I have to do back substitution, and so I have negative 1/2, 1 minus x squared 3/2 over 3/2 plus c. Well, you can simplify if you like, but you're done. Okay, so let's compare. So success, complete success. Problem solved. We have found the antiderivative of our function. Let's compare to that. It seems to be these two problems have so much in common. So what's the difference? The one at the top and the one at the bottom. What's the difference?
Variable of x was added to the one at the bottom before we started substituting.
Right. Right. It was there, so the function is different in a kind of seemingly minor way. There's an extra factor x, which actually makes it more complicated. Let's look more complicated, right? X, or there is no x at the top, and but it is that x that made everything possible, right? It is that x that canceled x later on, and that's why we didn't have to do any extra work, and we had the integral with respect to u right away. Okay, so that's the difference. That's when something doesn't work out well, because why? Because there is some term is missing, but you cannot just insert an extra term there because you want to. Because remember, we are not just practicing here. We are trying to prove indeed that the area of the circle is pi r squared. Okay, so we still have to finish this integration, but it turns out that our choice of substitution was not y's, and it appears that the plan that for using integration by substitution from calculus 1 actually fails altogether. The plan was, once again, you have a composition, break it into two, and the first step in that consecutive computation will be a new variable. Okay, so consecutive computation over here, this is the consecutive computation, and we take the first step, u is equal to 1 minus x squared as the new variable, find du, find dx, is carry out the substitution, and you have a new integral. Okay, so we did this, and we only failed in a narrow sense. We failed to solve the problem, even though we did succeed in substitution. So we did convert, and once again, I'm talking about the top. We did succeed in converting the integral with respect to x to the integral with respect to y, and that is sometimes the best you can hope for. Okay, but we did not solve the problem, and we really want to, so we need to find another substitution, and it turns out it is it's kind of unexpected. So we're talking about the integral 1 minus x squared dx. Okay, so u is not, the new variable is not 1 minus x squared. So this one we have to discard this possibility. The substitution is kind of goes in the opposite direction. Well, let's first examine the function. It is easy to forget where we came from, and where we came from is the circle. So this is our function y equal 1 minus x squared, which is, if you want to do implicit equation, it will be x squared plus y squared is equal to 1. Okay, so that's the implicit equation of the circle of radius 1, the whole thing, rather than only half of it. Okay. So the idea then is to actually utilize the fact that this is a circle, and there is some insight here, and the insight is that we're gonna introduce a variable that is not 1 minus x squared or anything like that. It is in fact the angle. So if this point is xy, okay, so this is the new variable. T is the new variable. So remember that we are trying to express x in terms of a new variable, as we have. Over there we expressed u, the new variable, in terms of the old variable x, and that was the formula that didn't work out. And now we are doing a similar thing, but we came up with this idea that the new variable should be, in fact, the angle between the point on the curve, which is a circle, and the x-axis. Okay, so this is my t. So it is hard to believe that such an awkward idea would work out, but it just does. Okay, so we are using the fact that it is a circle, and there will be some trigonometry, even though the original integral has none of it. But since it's a circle, well, we should be surprised that there is some. So, okay, so what is the substitution? What do we, I want to convert now my integral to an integral with respect to t. Okay, so it's really not that complicated. What is x in terms of t? Or t in terms of x, doesn't matter. What's the relation between x and t? Cosine, that's right. So it is a radius 1 circle. Okay, so t is the angle, and x is, where's my x? This is my x. This is x. So we have a right triangle with a known angle, t, and a known side adjacent to it, which is x. So the conclusion is then x is equal to simply cosine t. Well, as always in substitution, we just planning ahead. We could have dx. What's dx? Negative sine t dt. So whenever we're doing the second part of the substitution, we're going to need this. So we're taking our integral again, 1 minus x squared dx, and substitute integral 1 minus cosine t squared square root dx is negative sine t dt. Right? So one substitution, the other substitution. X here, dx there. Okay, so clear what has happened? So as you can see, there's a kind of a different, since we started with the new variable rather than ended with a new variable, we don't have to worry about it. We just replace every x, and there are no x's left. We have only t's as well as dt. So the integral is totally converted into a new integral with respect to t only. Okay, so we don't have to worry about it, but we do have to try to simplify, because right now it still looks kind of complicated, worse than the original. So starting with the numerator, starting with the first term, the square root. You see what this is?
So sine squared.
Yeah, inside. So it is, in fact, the Pythagorean theorem that says that sine squared t plus cosine squared t is equal to 1. Okay, so Pythagorean theorem with the hypotenuse is equal to 1 is this is the way to remember. The number one formula, number one by far, the formula in the whole trigonometry. Out of there are hundreds of them, but at least one you absolutely have to remember. That's the one. Okay, so and that's the one we're using. Okay, so indeed, then 1 minus cosine squared t is equal to, in fact, sine squared t. So we end up with integral sine t since we're talking about, I don't need the absolute value here because we're talking about the upper half of the circle, so sine is positive, so we don't have to worry about the absolute value. And here I still have negative sine t dt. I simplified, and I have negative integral sine squared t dt, which is really not very encouraging. But it certainly looks different from the original, right? Very, very much different, but it still has sine. So we brought trigonometry into this, which is maybe to our detriment, because it's still doesn't look simple enough for us to go straight ahead to integration. So if you have any ideas of what to do with it. So once again, you can find it in the back of the book, but they use trigonometry again. And the trouble with this formula is that sine squared is not something that we can integrate, even though it is once again a composition. And come to think of it, can you carry out the substitution with? No, you probably will get back. So you don't want to carry out the substitution, even though this is a composition, right? This is sine t squared, right? So you might be tempted to do a substitution. Why wouldn't you do a substitution? How about I choose this u? Seems like a reasonable idea. Why is it not going to work?
It'll just switch back and forth between sine and cosine all the time.
That's right. We would end up with pretty much the original integral. So once you introduce a trigonometric substitution, then you don't want to go backwards, and then because you will end up with where you started with no inevitably. So that we discard that again. So once again, this comes pretty much from experience, and you might actually at some point, if you carry out that substitution, to realize that it's not going to work. So just be prepared for that. That's okay. It's important actually to be able to carry that all the way through in order to discover that that was a dead end. Okay, so we just saved some time. But there is another formula for sine squared. Anybody remembers any idea of what we could turn sine squared t into? What? Well, there's a formula for the double angle. So it is definitely in the back of the book or in the beginning of the book. I think the inside the cover. I'm sorry. Excuse me. Oh, well, anybody with the book, can you take a look at the beginning of the inside the cover trig formulas? No, inside the cover. Oh, there is nothing inside the cover. Oh, okay, the back maybe. Okay, I guess that's typically they put it on the cover, inside the cover, right? That's the most of the book that I have seen, but apparently sometimes they are in the just in the back entirely. Well, anyway, I have the formula here, so we can just write it. It's simply 1 minus cosine 2t over 2 dt. Okay, so you can see how this is easier because the substitution becomes possible, right? I could just split it into two. I'll have integral negative 1/2 dt by the sum rule plus 1/2 cosine 2t dt. And finally, so the first integral is equal to what? Negative 1/2 x, yes. We are going to add c at the end, so let's not worry about that. Okay, so this is a constant function, so we integrate, we just add x to it, that's all. Now, what do we do with cosine, though? Cosine 2t, how do we evaluate it? That's right. So this one is an easy substitution, and that one works out every time. So u is 2t's, then du is equal to 2 dt. So then the substitution will be simply cosine u du, and there is a 1/2 somewhere, right? Yeah, over 2. Okay? So integrating cosine, the integral of cosine is what? Sine u plus c. Okay, so once again we have to work back towards, I'm sorry, that's not an x. I wish somebody stopped me. It's a t, right? So we integrate with respect to t, so it has got to be t over here. So the variables matter, right? Because we're going to now work our way all the way back to x. Okay, so the first step in that direction gives me, so this is still the same, 1/4 sine 2t plus c, and yet one more substitution is remember, x is, where is my formula? X is cosine t. Okay, so I do back substitution. I have negative 1/2 cosine t, and here it is, since we are almost out of time, let me just leave you with something that does not really look that good. Like this. So you see, the problem is we're done with integration, it appears. We express the answer as a function of t, the end, but unfortunately that formula, that second term over there, it looks so awkward that we probably won't be able to use it to actually prove what we care about, and that is that the area is, in fact, the answer should be pi over 2. So we'll do it next time.